Hello everybody, welcome to this video giving an introduction to some aspects of integral calculus with parametric curves. So let's get started. And the first thing that we always talk about when we're doing calculus, at least integral calculus with curves, is finding signed areas. So how do we do that with parametric curves? So let's suppose we have a parametric curve defined by x and y in terms of t. So x is a function of t, y is equal to g of t. Then the signed area bounded by the curve and the x-axis, I claim, is the integral of g times f prime of t dt. So why is this true? What's a way to think about this? So before, back when we had y in terms of x, this was the integral of y, whatever y was, with respect to x. So it was the integral of y dx, where y was some function of x, and we integrate everything with respect to x. So here it's the same because y is equal to g of t. And if we think about x equals f of t, dx dt is equal to f prime of t, that says that dx informally is f prime of t dt. So you can think about this as being the integral of y times dx, which is exactly what we had before, except now the dx we write as f prime of t times dt. Okay, so let's see an example. Of course, as usual, if here was the area bounded by the curve in the x-axis, if it's the area bounded by the curve in the y-axis, everything will be swapped around. So we'll be doing the integral of f times g prime of t dt. And it will be then the integral of x dy with the same motivation. Okay, signed areas below the x-axis, as usual, have a negative sign. So if we're finding area versus finding signed area, we have to be careful. If we want to find an area, which is always positive, and it's below the x-axis, then we're going to have to swap the sign. And also here, there is an extra strange thing. If the x is decreasing, that means if the curve is moving from right to left, then the integral will be negative, right? Because if x is f of t, so dx is equal to f prime of t dt, if the curve x is moving to the left, that means that f prime of t will be negative. So here we'll have something which is negative in the integral and the sign will be swapped. So if you want to find the area in that case, you're going to want to want to divide into areas where the curve is moving to the right and where the area is moving to the left. Or you can just look at the integrand, look at the thing you're integrating and see where it's positive and negative. And if you're finding areas, not signed areas, you want to make sure you split it up so you're integrating something positive. Okay, so for example, let's try to find the area under one arch of the cycloid, x equals r times theta minus sine theta, y equals r times 1 minus cosine theta. And this comes from a curve which is rotating across the x-axis. So here, one arch corresponds to theta running between 0 and 2 pi. So we use our formula, y is equal to r times 1 minus cosine theta. Remember, we're trying to integrate y dx. So dx here becomes r times 1 minus cosine theta d theta. So we have our y, we have our dx in terms of theta, so in terms of our parameter. So all we have to do then is integrate. So we're integrating y dx. Here y is r times 1 minus cosine theta. Dx is r times 1 minus cosine theta d theta. And now we can forget where this integral came from. It's kind of a messy integral. So how would we do this one? R is a constant. We can pull them both out. We have r squared on the outside. And then we have a bunch of things involving theta. If we multiply them out, we'll have some constant terms. We'll have some minus 2 cosine theta terms, which we can just integrate. And then we'll have a plus cosine squared theta term. And now we have to kind of cast our minds back to earlier in the semester. Cosine squared we can integrate by converting to double angles and then integrating to double angles. So those will be the steps. So if you go through that, in the end, you will get 3 pi r squared. So it's kind of stuff back from earlier in the semester, so I'm going to skip over that. So this is an example on finding the area bounded by a curve on the axis. Of course, we'll do more examples in class. The next kind of thing we might be interested in is finding the arc length of a curve. So suppose a curve is described by x is f of t, y equals g of t. Then the length of the curve is just the integral of the square root of dx dt squared plus dy dt squared dt. So this also is very similar back to what we had in Euclidean case, where we were doing the integral of the square root of 1 plus, excuse me, 1 plus dy dx squared dx. So let's see an example of how that works. So for instance, if x is cosine of t, y equals sine of t, t is running between 0 and 2 pi, let's try to find the length of c. So all we have to do is substitute everything in our formula. We get dx dt is negative sine t, dy dt is equal to cosine t. We substitute everything in. We're integrating from 0 to 2 pi. The square root of dx dt squared gives us sine squared t, dy dt squared gives us cosine squared t. Okay, that means the inside is going to be 1 using our trig identity. So we're integrating 1 from 0 to 2 pi. Okay, we get 2 pi. And this makes complete sense, right? Because we said that x equals cosine t, y equals sine t. It's the parametric equation for a circle with center the origin and radius 1. So it stands to reason the length should be the circumference, which is equal to 2 pi. Here, of course, it was kind of easy to simplify the square root, which is why I chose a simple example like this. But we had other techniques for simplifying square roots, right? We could try to pull a factor out and try to then make a substitution. Or we could try to write the inside as a perfect square by completing the square. And then if we have the square root of a perfect square, they cancel very nicely. So we're using exactly the same techniques we saw back when we did arc length with y in terms of x or x in terms of y. Okay, and then the last thing we might want to calculate is the surface area. So suppose we have a curve in parametric coordinates as before. So x is a function of t, y is a function of t. Then if we rotate the curve about the x-axis, here is a formula for the area of the surface. It's the integral of 2 pi y times the arc length element. So that's the integral of 2 pi y square root dx dt squared plus dy dt squared dt. And of course, if instead of rotating about the x-axis, we were rotating about the y-axis, then instead it would be 2 pi x times the same square root. So here's an example. Let's show the surface area of a sphere of radius r is 4 pi r squared, which is a formula that should be true. So how do we represent a sphere if we're in parametric coordinates and we're rotating? One way is to think about a semicircle and then rotate the semicircle around an axis. And we only want to rotate a semicircle because as we rotate around an axis, we're rotating through 360 degrees or 2 pi radians. If we start with a circle and we rotate 360 degrees, it's going to cross over itself. But if we start with a semicircle and rotate 360 degrees, we're going to get the exact sphere once. So a semicircle of radius r is going to be x equals r cosine t, y equals r sine t, and to have only a semicircle, t runs between 0 and pi. So then once we do that, we substitute everything in our formula. We have the integral of 2 pi y times the square root of dx dt squared plus dy dt squared. We know here that dx dt is minus r sine t. dy dt is r cosine t. We substitute everything in. So we have 2 pi r sine t. Here we can pull out the r squared, but it's inside a square root, so it's going to become r. So we get 2 pi r squared sine t. And then inside the square root, we have sine squared t plus cosine squared t, which is going to become 1. So we end up with 2 pi r squared sine t. We integrate the sine t, we get 2. So we get 4 pi r squared, which is exactly the right area that we know for the surface area of a sphere. Okay, so that about wraps it up for this video. We talked about finding arc length and area and surface area. And everything is pretty much back as when we had it with y in terms of x or x in terms of y. There are just some slight tweaks to those formulas we need to keep in mind if we're using parametric curves. Okay, we'll see more examples in class. Thanks everyone. See you next time.